This brings us to the concept of conservation of energy, which states that energy can be moved from one place to another and changed into different forms. Kinetic, potential, we'll find other forms later, but that the total amount of it stays the same. It's kind of like this apple. It can be a whole apple, it can be whole apple, or it can be apple slices, it can be apple sauce as we break it down into smaller and smaller pieces. However, the total amount of apple should stay there. Before, we just talked about kinetic energy and work, which was an energy transfer, and now we add into the mix potential energy. So if we have a situation where all of the forces are internal forces that happen to be conservative, so that we can write their works in terms of potential energies, then we'll be able to say that the total mechanical energy, this is mechanical energy, which is just the potential energy and the kinetic energy, is a constant. That means it's the same before and after interactions take place, or just different points in time, different things have happened. That total mechanical energy stays conserved. I could also write that as saying the potential energy of gravity, in this case, initial, plus the potential plus the kinetic energy at the beginning equals the potential energy at the end plus the kinetic energy at the end. So for example, if this apple falls down, then at the beginning I have potential energy, a high mgy, and very little kinetic energy, and at the end I have mostly kinetic energy and relatively little potential energy. If I add in a spring, then I simply have to add another potential energy term. So in this case I would have the potential energy from gravity, the potential energy from the elasticity of the spring, and the kinetic energy, and that total would be constant. So let's take a look at why that works. So we've already established the work-energy theorem, which states that the net work done on an object is equal to the change in kinetic energy. But what if the only forces acting are internal conservative forces? In that case, the net work is equal to the work done by conservative forces, and the work done by conservative forces is just minus the change in potential energy. In other words, plugging this in up here, minus the change in potential energy is equal to the change in kinetic energy. I can put them both on the same side and say that the change in kinetic energy plus the change in potential energy is equal to 0, or I can break them each up into their parts, so the change in potential energy is U final minus U initial, and that's equal to K final minus K initial. If we bring this through, now we can move the K initial over to this side, the U final over to that side, and I get exactly what I stated before, which is that the initial potential plus the initial kinetic is equal to the final potential plus the final kinetic. Exactly what we wanted. So the mechanical energy, referring to the potential energy plus the kinetic energy, is conserved. It has the same value at the beginning of a problem as it does at the end of a problem.